All right, so what we're going to do today, we're just going to take a look at a little bit of a review of linear, exponential, and quadratic models. Kind of take a look at the format of the 8.4 to 8.6 review assignment, and then we'll do our breakout meetings. Okay. Um, Make sure, like I said, work from 8.1 to 8.3 needs to be done today by the end of the day, including the quiz. And then any other work from chapter 8 needs to be done. Again, if you're trying to stay on track, the note check and the homework from 8.6, which was assigned on Tuesday, should be done already. Your review and your quiz should be done by the end of the weekend. Now, that's not saying put it off till the end of the weekend. Get it done as soon as you can. Always a good thing. All of the 8.4 through 8.6 work needs to be completed by April 28th. After that, I'm going to shut down all of chapter 8. So just make sure you have that all done. Again, your midterm grade is going to be based on what you've completed. So again, anything 8.1 to 8.3 that's not completed will be marked as missing, and most of it has been already. I think the quiz and the 8.1, 8.3 review have not. But everything else, if it's not done, it's missing. So, make sure you get that done. After today, the folder will no longer be red, it'll be gray for chapter 8. You can still access it, but make sure you've got that stuff done. All right, next week is a little bit different. Next week, because of the, they call it the pivot back to full in-person learning for those who signed up for the hybrid, teachers are being given extra prep time, and that prep time is coming in the afternoon. So class periods are adjusted. It will still be cohort A on Monday, Tuesday, cohort B on Thursday, Friday. But as you notice, the class periods will only be 50 minutes. So the kind of the bell schedule is a little bit different. I will have obviously these notes posted for you in Schoology, and these are actually on the 8.6 notes as well. So a couple places for you to see those. I think there was an email sent out to families also. Okay. All right, questions about that? All right, then let's talk about 8.6, linear, quadratic, and exponential models. Again, this is, I'm just going to review this rather quickly. This was from Tuesday's lesson, so hopefully you've got this all copied down into your notes already. All right, so a linear function, a function graphed as a line, again, straight line is kind of redundant, but that's okay, has a constant rate of change. Okay, so the equation, or an example of an equation, y equals 2x plus 1, so it has both x and y to the first power. So y equals 2x plus 1, that's that slope-intercept form, y equals mx plus b. You could also have standard form, ax plus by equals c. So that's the way you can tell in the equation form. If it's in a table, what you can do is subtract consecutive y values in your table. So take, and I always take the, I would go 1 minus -1, 3 minus 1, 5 minus 3. If those differences are all the same, it's referred to as a first difference, then you have a linear function. Your data is linear. That difference could be positive or negative. So just be aware of that. And the kind of the interesting thing, one of the interesting things is, notice the +2 here and the +2 there. That first difference is your slope. A graphing example, we have a line, slope of 2, y-intercept of +1. A situation that could be modeled with a linear pattern, something like Allie has $20 and can make $5 per hour babysitting her sister. How long does she have to babysit to have a total of $50? So there's a constant rate of change there, $5 per hour. So dollars per hour, miles per hour, things like that, feet per second are generally going to be tend to be more linear. Now, we have talked about feet per second in a quadratic model. It's a little bit different. We'll talk about that next. Questions on linear models? All right. Quadratic models, and this is where we've spent quite a bit of time this trimester. One way to describe or define a quadratic, it is a function that excuse me, a function that is graphed as a parabola. It has a U shape, and it shows increase and decrease in one of the variables. So if we look at the graph real quick, this shows the Y values are going down until you get to the vertex, and then the Y values go up. So that's the Y values increase and decrease and then increase. So that covers that part of the definition. An equation of a quadratic function is going to have an x squared in it. So one example, x squared minus 2x minus 3. We have that standard form, pretty common to see. We could have vertex form, which is over here underneath the graph. That we covered in 8.2, y equals a times the quantity x minus h squared plus k. Or the form we had in 8.4, intercept form, y equals a times x minus p times x minus q. Excuse me. If we have a table of values, what you'll notice, if we take the difference between y values, so -3 minus 0, -4 minus 3, -3 minus 4, we get our first difference, -3, -1, 1. They're not the same. So we take a second difference. -1 minus 3 is +2. 1 minus -1 is +2. The second difference is the same. If the second difference is the same or is a constant, then you have a quadratic function. Situation that would be described as with a quadratic function: John throws a baseball up in the air and wonders how high the baseball reaches. We call those vertical motion problems. So anytime something is being thrown, launched, kicked, dropped, tossed, those would be generally vertical motion and would be described with a quadratic equation. All right, any questions on quadratic equations? Then the new one, exponential equations. A function that is graphed as a partially curved line. So it's not like a parabola, which has that U shape. It's kind of part of a parabola and part of a line almost. And it shows very fast increase or decay. Decay would be the same as decrease of one variable. The easy way to see in an equation that you have an exponential function, x is the exponent. So f of x equals 2 to the power of x, that's exponential. It could also be written in with parentheses, y equals a times b to the x, and I actually prefer y equals a and the b to the x in parentheses. Just a bunch of different ways you can see it. I think this way that I wrote in red really reinforces the fact that the b is the only thing to the power of x. The table no longer has a difference pattern. Now it's a multiplication pattern. So in this case, we're multiplying by 2 to go from one value to the next. So one kind of tip, if you see one fraction and nothing else has fractions, or one decimal value in a table, that might be exponential. Now you should still double check, does it have a multiplication pattern, or does it have a first or second difference that are constant? So you just want to make sure. There are times when the base, the number that's to the power, is a fraction, and that would show decay, and it almost looks like we're dividing. So it might be like dividing by 2. Well, dividing by 2 is the same as multiplying by a half. So it's still that multiplication pattern. We're just multiplying by a fraction. The graph, as I said, starts it almost looks linear, and then goes up really quick after we get past x is 0. If it was decay, which I'll do in green, this would be kind of an example of a decay problem, but it would go like this. So it's just the mirror image of the exponential growth graph. Situations that can be described with an exponential function, how quickly mold grows in a petri dish. Anytime you see something that doubles or triples or quadruples over time, it's always being multiplied by something. That's exponential growth. It could also be multiplying by a half or a third or any fraction, any number between 0 and 1 over time. I believe in the notes on Tuesday, we had, I think, a car that depreciates by 12% of its value. Okay, so that's a decrease of 1% over time. That would be exponential. And then reproduction of animals, and the example here is rabbits, but it could be any animal or any population as far as that goes, would be exponential. All right. Real quick, quadratic functions in intercept form, which was 8.4. We saw this already on the quadratic functions page. The equation y equals a times x minus p times x minus q. The intercepts, remember I said just take the opposite of what's in that parenthesis with the x. The other thing you could do is solve it algebraically. Set the factor equal to 0, x minus p equals 0, and solve for x. You add p to both sides, you get x equals p. That's our intercept, p0. Do the same with q. In intercept form, you're going to find the intercepts first. Once you find the intercepts, then second, you'll find the axis of symmetry. And for the axis of symmetry, you add the x coordinates of your intercepts and divide by 2. The axis of symmetry is exactly halfway between your x-intercepts. And then just like with standard form, you take that value, that is the x-coordinate of your vertex, and you'll find that third. To find the y-coordinate, you plug that x into the original equation. Simplify it, and you come up with your y-coordinate. And as always, with any of our forms for quadratic functions, if a is positive, it means our parabola opens up. If a is negative, it opens down. If the absolute value of a is bigger than 1, it's going to be a narrower opening. So like if it was, if a was -4, it would open down and be narrow. If the absolute value of a is between 0 and 1, it's wider opening. You know, if a was positive 2/3, it would open up and be wide, wider than if a is 1. So things that you'll do in the review, identify the x-intercepts, axis of symmetry, vertex, and y-intercepts. And I believe those are just fill in the blank. So you'll type in the correct values. And there are a couple of problems. Oh, there's one problem like that. I thought there were two. Sorry. A little matching, match the graph to the equation. Notice on the matching there are multiple graphs. There are 6 and only 3 equations, so don't rely on process of elimination. There we go. Then convert from intercept form to standard form. In other words, multiply this out. You're going to use either the box method or FOIL. And then if there's a value in front, you'll use the distributive property. And you're going to fill in the blanks again. Now notice there is a sign already here. There's a sign already here. So if you multiply this out and you get, let's say, negative x squared minus 27x, you would just have to type in the 27. You don't have to do the negative. So the signs are there. And that should also help you if you get a positive coefficient in front of your x, go back and recheck your work. Okay, just be careful on that. Applications of quadratic functions. So we had 2 different types of applications. One was the area of a rectangle, where you again multiply using the box or FOIL method. You're going to get a function, which you'll fill in the blanks for the missing coefficients. And then we're going to plug in 6 for x and come up with the answer. Okay. So 2 different problems using this idea of a rectangle for area. The other type of problem we had with 8.5, we had pools with a deck around it we talked about. Here we have a flower bed in a city park that has red roses in the center and yellow roses on the outside. So again, here we're wanting to write the equation. So in standard form. And then if Julia makes the border of the yellow roses 5 feet wide, what is the total area? Okay. And notice the width of the yellow roses is your value for X. So you can certainly just use the function that you found in A. Then we have our vertical motion problem. And here's where I said, this is the one time where we had feet per second, and it was not a linear model, but we had other things as well, and that's why it's not linear. So we have our height, h of t, that just represents the vertical height at any time t, equals negative 16t squared. Again, the negative 16 is because of gravity, plus v sub 0 times t, where v sub 0 is your velocity, plus h sub 0, and h sub 0 is the initial height. So how high up were we before we launched the rocket, before we threw the baseball? How high up was the golf ball before it was hit? Things like that. A lot of sports applications or with vertical motion. And then t is time in seconds after the projectile is released or launched or whatever. So again, given some information, a rocket is launched from a height of 25 feet with an initial vertical velocity of 80 feet per second. Fill in the table, or fill in the equation, sorry, not the table, the equation. Find the maximum height, find how long it takes to get to the maximum height, and then find the maximum height. Remember, the maximum height and the time it takes to get to the maximum height are simply your vertex. It's your X and Y values of your vertex, X and Y. Then you will have to determine, looking at a graph, which type of equation it models. Is it linear, quadratic, or exponential? And that's a drop down. You'll just have to choose from the drop down menu. Match the type of function with the actual equation. Again, there are only 3 choices, but there are 6 functions. So you will have to use some more than once. And then finally, label the table. Is it linear, quadratic, or exponential? And that is the review. All right. Whew. Any questions? All right. Then what I am going to do